start. I'm sharing the screen. Just give me a minute. So today we are going to discuss assignment number 4, as you guys requested. So those who can't join, don't worry. We will have a separate session if you want, and if you want, then I can explain the solution the next session as well. So whatever way you want me to explain the solutions again to you, you can just let me know in the next session. And otherwise, the recordings will be uploaded on the YouTube channel, and you will get the link. And I will also share the notes, so don't worry about that. Okay, so let me start. So yeah, so it's our fifth live interaction session. And today's March 23. So yes, the first question says choose all the correct statements. So we are going to discuss assignment 4. Question number 1 is choose all the correct statement, and there are 4 options. The first question says choose all the correct statements where the first option is that R be a finite integral domain. Let R be a finite integral domain, and then R contains exactly one maximal eigen. Then R contains exactly one maximal. So I hope this question is easy. You can think over it for a while. Till then, I will write the second part. Yes. So the second part says let R contains exactly one maximal ideal, then R is a finite ring. Then R is a finite ring. So I can tell you that this is not a correct statement. So just try to think of an example, and till then I will write the third part. So third part says that I inside Z, where Z is a ring of integers, be a non-zero ideal, be a non-zero ideal, then the set of maximal ideals that contain I is finite. Then the set of maximal ideals that contain I is finite. So I think you already know what are all the ideals of the ring of integers. It's just the nz, where n is a natural number and also the zero ideal. So, but we are considering the non-zero ideals, so they are just uh, the multiples of n for a fixed n. Now you have to think that if we choose an ideal, non-zero ideal of z, then what can you say about the maximal ideal and the containment of that ideal? So it says that the number of maximal ideals that contain I will be a finite number. So for a hint, I can say yes, it is a correct statement, but you have to think that why is it so? Okay. And the fourth option is, if we consider the ideal and z, and suppose that there are exactly 23 maximal ideals containing I. Suppose that there are exactly 23 ideals uh, that contain there are exactly 23 maximal ideals, not just ideal, containing I. Then we have n less than equal to 23 power 23. So these are the first four options for the first question of the assignment. And I think you might have already guessed what the answer for the first one. So let me just write it. So we are given that R is a finite integral domain. So this phrase finite integral domain might be familiar with you, uh, might be familiar for you. So because we have already proved results regarding that in the lecture. Sir has already proved the results regarding that. So we know that a finite integral domain is a field. Okay, so that has been proved in the lectures. If you have any doubt, then you can go back and check the lecture notes and the recorded videos. Otherwise, you can ask me this in the next lecture. So it says every finite integral domain is a field, and now so we have that R is a field, and then the statement says R contains exactly one maximum ideas. So if R is a field, so R is a field, and hence has only two ideals, 0 and R. So by ideals, I definitely mean a two-sided ideal because we are in the rings with commutative rings with unity. So, and this also we have already seen that ring is a field if and only if it has only two ideals, 0 and the whole ideal, 0 and the whole ring. So, and you can easily see that if you take any non-zero ideal, then there is a non-zero element inside that field, and so its inverse is also there in the ring, and then you can just take say A is that non-zero element, so you can just say A inverse which is inside. So if A is there inside a non-zero ideal which is non-zero element, so as you are in the field, your A inverse is there inside the R, and by the property of the ideal, A inverse A belongs to I. This is from the ring, and this is inside the ideal, so this will be inside the ideal, and A inverse A is 1, so 1 is there inside the ideal, and that will imply that your ideal is the entire thing. So we know that all the possible ideals for a field is just the 0 and the entire field. Thus R cannot be maximal because in the definition of maximal ideal we assume that the ideal is not not the full R. So thus 0 is the only maximal ideal, because there is no ideal now between 0 and R. So 0 becomes a maximal ideal and there is no other choice of maximal ideal. So the statement is true. Okay. Now let's see the second statement. As I gave you the hint that the second statement is not true, so we should, if you can just find a counter example, then we are done. So it says that suppose that a ring R contains exactly one maximal ideal, and R is a finite ring. So, uh, so if you want that the statement is not true, then definitely we should think of a ring where you have uh, more than one maximal ideals, and the ring is infinite. So the first choice of an infinite ring is definitely the Z, and uh, you can try with that. It is also true for Z that there are more than one maximal ideals because the prime the ideas generated by prime numbers you can take. So we need to find an example which contains exactly one maximal ideal, but R is in fact infinite ring. So why Z will not work? Because because Z has plenty of maximal ideals, right? The ideal generated by each prime number is a maximal ideal there. There are plenty of maximal ideal. So it's although it's an infinite ring, but the hypothesis is not being satisfied. Okay, but typical there are very natural counter examples to it. You take any infinite field, say uh, R to be Q, the field of real numbers C, or any infinite then since R is a field, the only possible maximal ideal of R is 0, right? So hypothesis is satisfied, right? Thus, that the R contains exactly one possible maximal ideal, then R is a finite ring. So, but R is not a finite ring. You can see here, all the rings that are consideration are infinite rings. So the statement is false. Thus, the statement is false. Okay. Now let's see the third option, which says that I be an ideal of Z, and says that I be a non-zero ideal of Z in the set of maximal ideals that contain I is finite. Okay. So as the hypothesis says, let I inside the Z be a non-zero ideal, then what you have? Then you have that I is the ideal generated by some num integer n, non-zero integer. So then I is equal to nz for some n belongs to z. Okay, or particularly you can also choose n belongs to n, because anyway the plus and minus sign is not going to create a problem. Yes, for some n. So let n is equal to say p1 r1 p2 r2 dot 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 pk rk be the prime factor decomposition of n, then the only maximal ideals that contain I are p1z P2Z dot PKZ. Okay, so because later in the same set of exercises, we will see that if an ideal ideal of integers I is containing the ideal mz, then if I is generated by n, then m has to divide n. And here as we also need that the ideal that contains I is maximal, so we can only take ideals which are generated by the prime numbers. So the only possibilities are the prime numbers that are in the prime factor decomposition of n. Okay. Thus, the number of ideals number of maximal ideals sorry, that contains I is equal to the number of distinct primes that divides n. Since this number is finite, thus the statement is true. Okay. Yes, the fourth statement says let I be the ideal generated by n. Then suppose that there are exactly 23 maximal ideals containing I, when n has to be less than equal to 23 raised to 23. So don't be afraid of this big number 23 raised to 23 and don't try to evaluate it. It is of no use. So there is just small trick that you need to understand. So it says if I is an ideal, then there are exactly 23 maximal ideals containing, and suppose that there are exactly 23 maximal ideals containing I. So by the observations made in the question in the previous option, by the observations made in part 3, so let me see, there is exactly 23 or exactly 23 maximum. So by the observation made in 23 made in part 3, one can conclude that I equal to nz is contained in exactly 23 maximal ideals if and only if there are exactly 23 distinct primes dividing n. Okay. So why I am saying so? Because see, in the previous part you saw that the what are the maximal ideals that contains the ideals generated by n. It is precisely the primes that it is precisely the ideals generated by the primes that are dividing n. So if you have exactly 23 maximal ideals that contains I, that means there are exactly 23 prime ideals that would divide that should divide n. Okay, so that is the first thing we can observe about our n. Now, uh, let uh, so yes. Now we have to see that whether n is less than equal to 23 or not. Okay, 23 raised to 23 or not. So let p1, p2 dot p23 be those primes. Okay. Now, as n is arbitrary, so okay, those primes, and we say it is equal to P1 R1 P2 R2 dot P23 R. Okay. Now since n is arbitrary, arbitrary, thus we can take n Ri's as larger as we want, right? Because we just want that there should be 23 distinct primes dividing n. We don't uh, really care what those primes are. We can take those primes way much larger than 23, and these powers also this you can take as larger as you want. So right, thus there are many choices of n for which n is actually strictly greater than 23 raised to 23, or in fact, so um, yeah. So there are many choices of n for which n is actually greater than can be greater than 23 raised to 23. Thus, you can see that the statement is false. Thus, the statement is false. Okay. I hope this is clear. We are not doing anything non-trivial here. All you need is to just understand that what kind of uh, ideals, what kind of values of n you need to satisfy the hypothesis. And once you understand the concept, then to arrive at a contradiction is a trivial point. Okay. So that concludes the first question of assignment 4. So let me just write the second question, or if I can just copy paste from somewhere, then it would be nice. Yeah, so I can do the copy cut paste thing. So it will definitely save the time. So yes, the second question says that R be any ring and Ij be the ideals. So we need to choose all the correct statements. And here, as usual, Z denotes the ring of integers. So the first statement says if I plus j is R, then Ij is equal to I intersection j. Okay. So yes. So let us. This has been proved in the class as well. So the statement is true, no doubt in that. The proof you should have seen in the class itself. So the statement is true, and the argument to that is so. First of all, let us see whether Ij is contained in I intersection J or not. So claim first, and one can see that this is always true, that Ij is contained inside I intersection J. You even don't need the hypothesis that I plus J is equal to R. Uh, when we will try to prove it, you will definitely realize it. There is no need to assume I plus J is equal to R. So what are the elements of uh, Ij? So let X belongs to Ij, then X is of this form, summation of Ri Si. Yes, maybe we can just prove it. Yes, I is equal to 1 to n, such that Ri belongs to I and Si belongs to J. Okay. Now see, each term in this sum is of the form say Rk Sk, where Rk is inside I and Sk is inside J, right? So this thus Rk Sk belongs to I intersection J for all 1 less than equal to k less than equal to n, because i's and j are ideals, so they are closed with respect to multiplication from the elements of the ideal. Okay, so rk sk is inside I and it is also inside the j as well, and this implies that x, which is just the sum of these elements, is also inside I intersection j, and thus the one side complement is here. As a point of caution, I will just mention this thing. We don't need I plus j is equal to R for proving this. Okay, so sorry for this. The second part actually need I plus j is equal to r. So let me try to prove the second part. In second, Ij contains pi intersection j. Okay. So let some x belongs to pi intersection j. Then what you can get it from there that ix belongs to I and x also belongs to j. Now uh, you can write x is you can write x as x dot 1. Okay, and since 1 belongs to r, which is equal to I plus j. Just write it later. So since 1 belongs to r, which is I plus j, therefore there exists some r belongs to I and some s belongs to j, such that 1 is equal to r plus s, right? Now you see that uh, the x is just x dot 1, which is x dot r plus s, and that is nothing but x dot r plus x dot s, not r dot s, it is x dot s, and you can write it as r dot x plus x dot s. So this r is inside I, right? And x is inside I and j, so definitely it is inside j. X is inside I and j, so you can now consider it as an element of I, and x is inside j, so this will definitely be inside ij. Okay, write it a bit neater. So this definitely implies x is inside ij. Thus, we have I intersection G lying inside ij. So hence, the claim is established, that is ij is equal to I intersection G. So just see that the first part is okay for any uh, ring, but the second part required that the ring is a ring with commutative ring with unity, and also I plus j is equal to r. Okay, so just try to see what assumptions we are using for proving a statement. So if you remove the assumptions, then what happens? Okay. Okay. So the second part is just a converse of the first one, which says that if I plus j, if ij is equal to I intersection j, then I plus j is equal to r. So we have a counter example for that. Not a single one. You can just think of many counter examples, but I'm just writing here one of those. You see, solution of B part. So consider this ring. ring ring of polynomials over Q in two variables x and y. So let R be Q x y. Okay. Now we need two ideas which contradicts the which satisfy the assumption but contradicts the conclusion. So you just choose the obvious ideals I to be the ideals generated by x and y j to be the ideal generated by y. So now you can see that I ij is nothing but, so yes, let me just uh, try to see it. So what are the polynomials that are inside I and that are inside j? So now I generated by x is nothing but the set of all polynomials of this form fxy dot x such that fxy is inside q of xy. They are all they are the polynomials which has uh, uh, x as a common x as one of the factor. Okay, and j is the ideal generated by y, and it is definitely the polynomial y. In that's right. We'll just change the notation. So it is the set of elements which has y as a common factor. Now, what is I intersection j? I intersection j is a set of polynomials which are in x and which are in y. Sorry, which are in I and which are also in j. So these contains the set of all polynomials fx, sorry, xy, hxy, such that hxy belongs to q of x comma y, right? Or in other way, you can say that this is the set of polynomials divisible by the polynomial xy. Okay. Now you can clearly see that clearly I okay correct. Ij is equal to I intersection j because let me just think for a moment. So we are taking R to be the polynomial ring in x and y, I to be the ideal generated by x, and j to be the ideal generated by y. first we need to check that whether ij is equal to I intersection j. So I intersection j is definitely the polynomials which are in I and which are in y. So they are the polynomials having xy as a common factor. Now, uh, what is I plus j? So I plus j is contains the polynomial, say some fi of x comma y and gi of x comma y, such that fi are inside I and gi are inside j. Okay, and I is equal to 1 to say k, and k also vary. K is inside natural number. Now, since fi belongs to I is divisible by I is equal to x times some say f I delta, right? This is one thing, and also you have gi inside j. Therefore, gi is equal to y times say some gi delta, right? For some fi delta inside the ring of polynomials in two variable, right? But this implies that your I plus j is nothing but, now you can take x and y common. So let me just write it first. So this is xy times fi delta of xy gi delta of xy, and then you have the same hypothesis, right? The gi and fi are in qx. But this is same as saying that it contains polynomials which has xy as the common factor. So let's say this is some xy, um, out of notations. So what notation I should use? I have already used f, g, and h, fi, gi. So maybe k is already there. So let me just come up with something. So f xy, say polynomial p in xy, such that p of xy belongs to p of x comma y. And this is precisely what we were getting while computing the expression for the elements of I intersection j. Xy, hxy, hxy belongs to qxy. So this is varying over the entire q xy, and then below part is this is also varying over the entire ring q. So thus your I plus j is nothing but I intersection j. But you can check that I plus j is not same as R. R is definitely the Q, and the reason is you have plenty of elements. Like you just pick an element which is not divisible by x and y both. So you can just see that x, y, one, any constant polynomial x, y, or Any constant polynomial you can take. This is not inside I plus j, right? And there are many others. You can just take alpha times x, alpha times y, any alpha times x raised to I, alpha times y raised to I, anything you can take which is not divisible by x and y both. Then this says that the statement is false. Okay, now so let us see the third statement also. So this says suppose that I plus j is equal to r, then we have a ring isomorphism R isomorphic to R modulo I plus R modulo J, where the right hand side ring is the product of ring of the two quotient rings. So in the class, there is a slight variation of this statement was done, and now this statement is in front of you. So the answer is false, and let me just give you some example to just believe that. This is equal to. Let me just write the example. This is the C part. C part is uh, not true, so we just need to give an example and we are done. So the statement is definitely false. The counter example you can take is our favorite over our favorite ring R to be integers, and I and j units such that I plus j is equal to R. So you take R I to be 2z, j to be 3z. Then you have I plus j is equal to R. But you look at the right hand side of it, what is R modulo I? Yes, the right hand side. R modulo I cross R modulo j. But R modulo I plus R modulo j is ry. R is z. Z what 2z and with z what 3z, right? And this is a finite ring. This is a finite ring, right? And R is z, which is definitely an infinite ring. So R cannot be isomorphic to R mod I, R mod J in this case. So this serves as a counter example. Okay. But uh, the correct statement is, let me just write it. The correct statement is R modulo I intersection J is the corrected statement is R modulo I intersection J is isomorphic to R by I cross R by J. Okay, and this has been proved in the class in the lecture notes. This has been proved in the lecture notes. The lectures. Okay, so yes, the statement is false. We have an counter example for that. Now we have to see the D part, which says that let R be the set of ring of integers and Ij be the non-zero ideals of Z. Then suppose that Ij is equal to I intersection J. Then we have I plus J is equal to Z. Okay. So we see we have already seen that this kind of statement is not true in general because B serves as a counter example for we saw a counter example in B. So they're also like it's saying if Ij is equal to I intersection J, then I plus J is equal to R. So we got a counter example in B, right? Now, but this is true if we take R to be Z, right? So this is there is a point of caution here. Don't guess it from what we got in the part B. There we are getting a situation for a particular ring, but so this statement is not true in general, but we might get the positive answer for another chosen ring. Integers, and for the integers, this kind of statement is true. So let you take I to be m times z and n to be sorry j to be n times z, where mn are integers, right? Now uh, what is I plus j? Let me write I plus j as positive integer, because anyway you can take them to be positive. The minus sign is not going to do anything. So you take I plus j to be n. There is no issue with that. Now, what is I plus j and what is I intersection j? So I plus I intersection j will be the number, say alpha of n, where alpha is the LCM of m and n. Okay, this is easy to see. See, something belongs in I and something belongs to J. What does this mean? That this is divisible by M and this is divisible by N. So they are divisible by M and N both. So they are divisible. So that number is divisible by the LCM of M and N also. Thus, I intersection J is contained inside alpha of N. And definitely, as alpha is an LCM of M and N, so M and N both divides alpha. So alpha is inside I and alpha is also inside J. Thus, alpha n is also contained inside I intersection J. Thus, we have I intersection J to be same as alpha of n, where alpha is an LCM of Mn. Now, what happens to I plus J? So also I plus J is, so one can check this also. Sorry, Ij is equal to Mn J. Okay, this is easy to see. See, definitely Mn J is contained inside Ij, because uh, let me just say some words over it. Any number Mnx, you can take it as, say, yeah, m times nx. Now this number is inside J, and this is anyway inside I. So this is x, and this is your m. This belongs to Ij. Oh, this belongs to Ij for all x in Z, right? And this definitely implies that the wing, that the ideal M and Z is inside Ij, right? Now, for the other containment, uh, say R, if R is inside Ij, then R is the summation of some alpha I, beta I is equal to 1 to n, and where these alpha i's are inside I and beta I is inside J. Now, since alpha I is inside I, therefore alpha I is some Ri times alpha bar. Sorry, this is because it is inside I, it has to be divisible by m. This is m times alpha I bar for some alpha I bar inside I, right? And beta I belongs to J, we implies that beta I is equal to some n times beta I bar belongs to J for some beta I bar belongs to J, not J, it should be Z. Okay. So that's what you can say from here. This implies that you have R as m n times summation of alpha I bar beta I bar, where I is from 1 to I overuse this notation and I should not have done this. So I will take a k here. Okay. Now what? this is definitely inside Mn inside, right? So you see that we take an element from Mnz, and then if we show that it is inside Ij, and then we take an element inside Ij and show that it is inside Mnz. So the equality is there. So Ij is Mnz. Now, if we want that Ij is equal to I intersection J, if Ij, which is nothing but Mnz, if we want that this is same as I intersection J, which is nothing but the LCM of Mn Z, right? This is this. Okay. Then Mn has to be the LCM of Mn, and this is possible if and only if Mn and are co-primes, co-prime numbers, right? But if Mn and are co-prime number, then what can you say uh, about I plus j equal to r? So this is true if and only if there exists some d and l inside z such that you can md plus nl, so, mm, is equal to 1. So this means that m and z are co-prime number. This means that the GCD of mn is equal to 1, right? This does means that. So GCD of mn is 1 implies that there are two integers d and l such that md plus nl is equal to 1. And this holds if and only if z is mz plus, write it separately. So instead of if and only, let me just use the single implication because that will confuse you. This implies uh, your 1 belongs to I plus j, and which implies that the entire ring, which is z, is nothing but I plus j. Okay, so you see that the statement B might be true in some other cases. We have examples, counter examples in some case, and then we have the positive examples for in the positive case in some other. We have the positive answer in some other case, so that might happen. So this is not true in general, but it is true for certain things, and Z is one such thing. Now let us just see the next question. If you have any doubt, then please let me know. Uh, Otherwise, I will just copy the third question and we'll start discussing it. Okay. So there are no responses. So I mean, it's clear. Now let us see the question number 3. It says that Z denote the ring of integers and QC denote the field of rational numbers and complex numbers. I denote the square root of -1, and Zi is the uh, smallest subring of C that contains Z and I, or the ring of Gaussian integers. And F is the field of fractions of this ring of Gaussian integers. Then one has to choose all the correct statements. So first statement is this field of rational number is contained inside the field of fractions of Zi. Second is minus iota is inside the field of fractions of Zi. Third says root 2 is there inside field of fractions of Zi. And fourth says that the field of real numbers is inside it. So let us see those statements one by one. So the first statement says that Q, which is a field of fractions of Z, is inside F. So see, you have the ring of integers Z strictly inside the field of fractions Fi, right? Or sorry, you have it inside Z of I. So see, if one ring is contained in the other, then the field of fractions of one ring could also be contained in the field of fractions of other ring. Because you here you would be taking numerators and denominators from this Z, and here you would be taking numerator and denominator from this Z I. So that's why if the ring is one ring is contained in the other, then the field of fraction of the first ring would be contained in the field of fraction of the second ring. So therefore, the field of fractions of Z is contained in the field of fractions of Zi. So yes, this implies. So what is the field of fractions of Z? So the field of Q, right? So Q contained inside. The first part is true. Now, what is the second part? Second part says minus of iota is inside F. So since iota is inside F, therefore minus of iota is also inside F, since F is a field. So it has to be closed under. So minus 1 is there. So minus 1 times iota would also be there. And minus iota is just the inverse, additive inverse. In that sense also you can see. So this is true because F is a field. So definitely an additive group under addition, and thus if iota is there, then minus of iota has to be there. So the first two statements are true. Now let's see the third statement. So see, if the fourth statement is true, then third has to be true, right? And if the third statement is not true, then fourth would not be true. Yes. So if we prove that third is not true, then fourth is not going to be true. Or if we prove that fourth is correct, then we prove that third is not. Third is also correct. So I will show that third is not correct. That's why third and fourth they both are not going to be correct. So yes. Uh, so let us assume that root 2 is inside F, right? Then we can write root 2 as A plus BI and C plus DI, right? So what are A, B, C, D here? They are going to be the integers. So A, B, C, and D, they are just integers. Then see, you can multiply, try to rationalize this, because we want to remove this eta term in the numerator, sorry, denominator. So we just rationalize it by multiplying it by d c plus c minus d eta, multiply, instead of writing it, I will just do it. So root 2 is a plus bi, and here you have c plus di. So you multiply both sides with c minus di and c minus di. Okay, you can do this because c minus di is non-zero. If that you can see, because if c minus di is 0, then c is 0, d is 0, then c plus di is also 0, which makes this term undefined. But you have root 2 here, so c is non-zero, d is non-zero, thus c minus di is also non-zero. Okay. So after rationalizing it, what you get? So you will get that this is equal to AC plus BD divided by C square. So all these calculations are similar to what we do in complex numbers. So there is nothing dif dif difference between this and the calculations inside the for complex numbers, because this field is going to be going to lie inside the field of complex numbers only. So this is BC minus AD divided by C square plus D square item. Okay, so just compare the real part and the non-real part. So this make us come to the conclusion that root 2 is same as AC plus BD divided by C square plus D square, and BC minus AD is C square plus D square is equal to this 0. Sorry. This part is of no use for us, the second observation, but see this part. Here you have A, B, C, D, all are integers. And this implies, so the root 2 is a rational number. Which is a contradiction. So root 2 is not going to lie inside your field of fractions. Okay. So this implies root 2 is not inside the field of fractions. So the statement is false. And in the fourth part, we just need to check whether R is there inside the field of fraction or not. So since root 2 is not there inside F, therefore the field R cannot be a subset of F, right? So this statement is also okay. So till now we have completed 3 questions of assignment 4. So if you have any doubt in that, you can just let me know. You can think for a few seconds. Otherwise, we will start looking at question number 4. Okay, so let's start solving the question number 4. So it says, let Z be the ring of integers and I be the ideal generated by M and J be the ideal generated by N. Then we have to choose the correct statements. So I intersection J is M and Z. So this statement is not true in general. This is true only when M and N are co-primes. So the first statement is false. The second is true. So let us just write them. So for A part, you can take I to be 2Z, J to be 4Z, then what is I intersection J? I intersection J is nothing but 4Z, which is not at all equal to 2 times 4Z, right? So the statement is clearly false. Okay, so let's look at the second part of it. It says if I intersection J is equal to M and Z, then M and N are co-prime. This kind of thing we have already seen in the above uh, uh, discussions. So let me just write it. If I'm sorry, let me just rewrite the statement in the most in a better way. So let we have I intersection J to be the LCM of Mn, the ring generated by this, right? This times Z. So if I intersection J is equal to M and Z, then what happens? Then you have LCM of M and N to be exactly equal to Mn. And this is true only when M and N are co-primes, right? So we have seen these things before, so I don't think there should be an issue in that. But still, if you have doubt, then you can just let me know. Okay. Third statement says if I plus J is equal to Z, then M divides N. Yeah. So this is also false. You can just see the example as this statement is true. Now let me write this. So I plus J is equal to Z. What does this mean? This means it's saying that M divides N, but this is not true in general. So you can take M to be say 5, N to be 6, then or in fact you can take M 5 or 6, there is no issue, but for the sake of convenience, let's say M to be 6 and N to be 5. Then 6 minus 5 belongs to I plus J. And this is what? This is equal to 1. And which implies I plus J is equal to Z. But clearly, uh, M N does not divides M, right? So this statement is false. Okay. Now, the last statement, which says I contained in J implies N divides M. Okay. So this statement is true because let I be inside I, which is MZ, be inside uh, J, which is NZ. Then M is also there inside J, right? Which implies M is equal to N times alpha for some alpha belongs to Z. And this is the definite, this is what we mean by the division, right? So this implies N divides, right? So this statement is of course true. Yes. So we have completed the fourth question. If you have any doubt, then you can ask. Otherwise, we will move on to the question number 5. Just have a look at the solution for a moment, and if you think that there is any confusion, then just let me know. So I hope it is clear. So let us start discussing the next question, which says that R be the field of real numbers, and this R is the ring of polynomials uh, over the ring of real numbers within infinitely many variables. Okay, so number of variables here are not finite, so it's in infinitely many variables. Then let I be the ideas generated by the squares of these variables. So I is generated by x square, x1 square, x2 square, dot 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 x. As it's a ring in infinite variables, so we will continue this. So I is generated by x1 square, x2 square, x3 square, so on. And you can check that it's an ideal in R. Now one has to choose the correct statement. So the first statement says ring R contains exactly one maximal ideal. The second statement says ring R contains infinitely many maximal ideals. So definitely one of them is true and one of them it has to be false. We have to see whether any one of them is true or not. The part C says the quotient ring R by I contains exactly one maximal ideal, and the part D says the quotient ring R by I contains infinitely many maximal ideals. Here also one of the statement has to be false. We have to see what about the other. So what this question actually tries to say that what's the aim of this question is you see first of all whether R has what how many maximal ideas R has, and then then also if the third four part says what how many maximal ideas does R by I has. Okay, so this question is there so that you guys get familiar with the ring in infinitely many variables and what kind of conclusions you can have in that ring. So yeah, let us start with solution one, solution of this question. So say if I could prove part B, then A is already false. So I will show that part B is correct, that it has infinitely many maximal ideals. Then R has infinitely many maximal ideals. Then of course the part A is false. Okay. So what you can do, you can take this ideal, take J of A to be the ideal generated by x1 A, x2, x3, dot dot dot. Estimate minus, yeah. So here A is nothing but a real number. Then JA is a maximal ideal of R. This implies there are infinitely many maximal ideals there are infinitely many maximal ideals of, because for each choice of real number you have a maximal ideal. So thus the B part is true, and this implies part B is true, and A is false. And A is false. Okay, so we have two more parts of this question. So there we have to see what happens to the ring R modulo I. I is already given to us. So let's have a look at that as well. Um, yes. So the question, it says the quotient ring R by I contains exactly one maximal ideal, or the quotient ring R by I has infinitely many maximal ideal. So here I will show that C is correct, that there is exactly one maximal ideal containing the I. So ideals, more precisely, I will say maximal ideals of R by I. We know that they are in one correspondence with the maximal ideals of R that contains I, right? But I here is the ideal generated by x1 square, x2 square, and then you have dot 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 to the it's the square of all variables, right? So let J be a maximal ideal of R that contains I. Okay. Yeah. So just give me a moment. So yeah, sorry for the pause. Yes. So what I want to say that if J is a maximal ideal that contains I, so then definitely it will contain the squares of all the variables. So let J be an ideal that can of I that contains I. So I is nothing but the variable square of all these variables. So yes, then we also know that each maximal ideal is a prime ideal. Then J is also a prime ideal containing xi squares for all I belongs to n. This implies J contains xi's for all I belongs to n, since J is a prime ideal. Yeah, but what does this mean? This means that J contains the ideal x1, x2, dot 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 dot. right? And J is also maximal, so J cannot be equal to R, right? But this ideal x1, x2, dot 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 is itself a maximal ideal that you can check is itself a maximal ideal. Thus, J has to be same as this. So J contains a maximal ideal and J is not equal to R. So J has to be that ideal. This implies that C is correct. C is true. Sorry. This implies that C is true, but D is false. Okay. Yes. So with that, we have finished 5 questions. Now let us just solve the 6th question and then we will stop. So if you have any doubt till now, then please ask. Otherwise, I will move on to the next question. Okay. Solution 5 is completed. I have written this. So if there is no doubt, I will assume that you have understood the solution, and thus let me just try to prove, try to show the try to solve the 6th question. So it says choose all the correct statements. R denote the field of real numbers. If R is a Noetherian ring, then every ascending chain of ideals I1, I2, I3, so on stabilizes. And if R is a Noetherian ring, then every descending chain of ideals I1, I2, I3 stabilizes. This is part B. Third part is the ring R is a subring of a Noetherian ring, then R is Noetherian. That means the subrings preserves the Noetherian property, that what C says. And the B part is the quotient ring Rx modulo x square is Noetherian. So let's start with the part 1. Solution A. So we define a ring to be Noetherian if every ideal of it is finitely generated. Okay. So the first statement is true, and you can check that every ideal of a ring is finitely generated. This happens if and only if the ring satisfies ascending chain condition, which means that any ascending chain of ideas stabilizes. So these things are if and only if. So we just try to see that it's just an equivalent definition of Noetherian. Uh, if it is, if you can't get it, then just let me know. Uh, we will discuss it in the next session. Okay, but for B, we have a counter example that another indeed need not satisfy the descending chain condition, and for that you can take again go with your favorite uh, uh, example. Let R you can take to be Z, then R is Noetherian. R is a Noetherian ring, and the chain we should give a descending which is not stabilizing. So you can give this chain generated by any prime, say uh, P. So, we want that any descending chain of ideas stabilizes, but you can just go with this chain instead of P. Also, you can check your that you can take any N. So the ideal generated by N contains the ideal generated by N square, and this containment is also strict containment, because N square can't be there inside your sorry N cannot be there inside the ideal generated by N square. Yeah, so we'll have N square, then it contains um, ideas generated by N cube, and so on. This where N is just say some natural number you can take. I have no issue with that. And the chain is an descending chain of ideals which is not terminating. So it won't stop anywhere. So that's why it doesn't satisfy the descending chain condition. So the statement is false. Okay. Yeah. So the third statement says that if R is a ring of and if R is a subring of another ring, then R is also uh, uh, another ring. For that, you can take this example. There are plenty of examples, but let us go with this one. The C part is take. So first of all, to give a counter example, you must have a ring which is not Noetherian. So you take R to be this ring, take R to be Z in infinitely many variables. Is not Noetherian, right? and if you take its field of fractions, then that field of fraction has to be Noetherian because it's a field. Then the field of fractions of R is Noetherian. Thus, C is false. Okay. Let's quickly see the D part also. The quotient ring Rx modulo the ring ideal generated by X square is Noetherian. So this is true because by the correspondence theorem, I have already stated the correspondence theorem above by dealing with one of the problem. So by the correspondence theorem, what you have since Rx is Noetherian. Rx is Noetherian because R is a field, implies Rx is a PID, and that will implies Rx is Noetherian. I hope you get it. So Rx is a Noetherian and Rx modulo x square. So if you take any change in Rx modulo x square, it corresponds to a change in Rx that contains, such that each element of that chain contains x square, and since that chain stabilizes, you have that the initial chain that you took in Rx modulo x square that also stabilizes. So by the correspondence theorem, since Rx is Noetherian, Rx modulo x square is also Noetherian. Okay, so this statement is true. So with this, the solution for assignment 6 is completed. If you have any doubt, then you can ask me. Otherwise, we will stop the session here. I hope if no one is responding, then it's clear. So I stop it here. See you on the next Friday from 6 to 8. Okay. Goodbye then.